Friends, welcome to the tutorial series on network analysis made simple. Laplace transform is a very useful tool introduced by a French mathematician called Pierre Simon Laplace. Friends, Laplace once said, quote, "What we know is not much, but what we don't know is enormous." Unquote. That was great Simon Laplace. Laplace was born on March 23rd in 1749. Despite of his family's poor financial conditions, he excelled in the area of pure mathematics and mathematics applied to astronomy and solar systems. He developed a conceptual view of evaluating the change in the structure of solar system. He also did pioneering work in mathematics regarding theory of probability and statistics, which influenced a whole new generation of mathematicians. He popularly and famously was known as a French Newton. Friends, I am extremely happy to dedicate this tutorial to the legend of mathematics, Pierre Simon Laplace. Friends, generally, electrical quantities like voltages and currents are time dependent quantities that you know. Especially in AC circuits, you know that when time varying excitation is applied to a network, a time varying response at the output is observed. We also know that when the time response of an electrical network is required, the balance equation for the circuit turns out to be an integral differential equation. This we learnt in the previous tutorials on classical approach to transient analysis and evaluation of initial conditions and final conditions in RL, RC and RLC circuits. Of course, the solution of differential equation will give the time varying response of the output. Sometimes the solution of the differential equation without adopting the classical approach becomes very tedious. It's tedious because first we require to identify the differential equation. For example, its order, whether it is first order or second order and so on, its type such as homogeneous or non-homogeneous and so on. Later, we are required to find the general solution and particular solution by incorporating the initial conditions. The solution becomes more complicated as the degree of differential equation increases. Laplace transform under such conditions becomes very much handy. Then we shall see what is a Laplace transform. Friends, generally if I ask students this question, most of the time I get the answer as, "Sir, Laplace transform is L of f of t is equal to integration 0 to infinity f of t e to the power of minus st dt." Friends, in my opinion, it is an equation for the Laplace transforms of a function f of t. So, my answer is the Laplace transform is a mathematical tool to transform a time domain equation into a frequency domain equation. We shall learn more details as we proceed further. Friends, you know what logarithm does? It converts multiplication and division problems into a simple addition and subtraction problems, and anti-logarithms are used to carry out the inverse process. Similarly, the Laplace transform converts a time domain differential equation into a frequency domain algebraic equation. Note that. And inverse Laplace transform does the reverse process. You know that it is easy to solve an algebraic equation rather than a differential equation. But After solving a transformed form of algebraic equation, the solution will be in the frequency domain. To get the time domain solution, we have to apply inverse Laplace transform, which I'll learn more as we proceed further. Friends, let me summarize the steps to use Laplace transforms. The first and the foremost is, given the network, write the balance equation which will be in the time domain and will be integral differential equation. Then transform the differential equation using Laplace transforms so that the differential equation turns out to be an algebraic equation. Next, solve the algebraic equation for the required parameter, and finally take the inverse Laplace transform of the solution to get the time response if required. Friends, let us now define the Laplace transforms. We know that a transform in general is a change of mathematical description of physical variable to facilitate easy mathematical solution. For example, we know in many electrical system equations, variables like voltage and currents and time appear. These variables are transformed into different domain using Laplace transforms. Hence, Laplace transform is defined in the form of a mathematical identity as L of f of t is equal to capital F of s is equal to integration 0 to infinity f of t into e to the power of minus st dt, where f of t is a function of time t and t is defined for t greater than or equal to 0. Note that. Then the Laplace transform of f of t is denoted either by L of f of t or capital F of s. Note that. If the integral which we defined in the equation of Laplace transform is an improper integral, you know that an improper integral may converge or diverge depending on the integrand. When the improper integral is convergent, then we say that the Laplace transform of f of t exists. The values of s for which the Laplace transform converges is called as the region of convergence. The concept of region of convergence can be understood easily by finding a Laplace transform of a function x of t is equal to e to the power of minus at for t greater than or equal to 0. By taking the Laplace transforms, we can write capital X of s by definition is equal to integration 0 to infinity x of t into e to the power of minus st dt, and that is equal to 0 to integration from 0 to infinity e to the power of minus at into e to the power of minus st dt, and we get integration 0 to infinity e to the power of minus into bracket s plus a into t into dt. But we know s is a complex frequency which is s is equal to sigma plus j omega. By substituting for s, we get capital X of s is equal to integration 0 to infinity e to the power of minus into bracket sigma plus j omega plus a into t into dt, and that is equal to 0 to infinity e to the power of minus into bracket sigma plus a plus j omega t into dt. The above integral converges if and only if real part of sigma plus a is greater than 0, that is, real part of sigma is greater than minus a. This value of sigma defines the region of convergence. Since we deal with functions for t greater than or equal to 0, we avoid the explicit mention of ROC. Hope you have understood it. Since S is a complex frequency, it should be noted that when the Laplace transform of a function f of t, which is in the time domain, is taken, we get capital F of S and it will be in the frequency domain. In other words, when the network is transformed using Laplace transforms, the time varying quantities in the network are transformed into frequency domain, and the solution obtained by solving the network will be in the frequency domain. Hence, note that analysis of circuit could either be done in the time domain directly or in the frequency domain after transforming the given network using Laplace transform. For convenience, Laplace transforms of some of the useful functions are listed for ready reference in the table shown. Friends, hope you have already learnt to find the Laplace transforms of these functions in your mathematics course. Note, all the functions listed in the table are represented without multiplying by unit step function u of t, as we explicitly declared that t is greater than or equal to 0. This aspect I will clarify when we deal with unit step function in the subsequent tutorials. Now, we shall find sum of the transform of some simple functions of t. Let phi of t and I of t be the excitation and the response of an electrical circuit. Then we know the Laplace transform of phi of t is capital V of s and the Laplace transform of I of t is capital I of s. Note, the time varying quantities V of t and I of t are represented by small letters, whereas their Laplace transforms are represented by capital letters, capital V of s and capital I of s. To clarify, consider few examples. First, let V of t is equal to 2 volts. What does this mean? The voltage V of t is equal to 2 and is constant with respect to time as shown in figure. So, its Laplace transform is capital V of s is equal to 2 divided by s. How did we get this? If you refer the table, you find that the Laplace transform of f of t is equal to a is capital F of s is equal to a by s. Here a is equal to 2. That is simple. Next, let I of t is equal to 2t amperes. You know what is this function? This function is a straight line having slope equal to 2 and passing through origin as shown in figure. Remember, we consider all functions for t greater than or equal to 0. So, the Laplace transform of I of t is equal to 2t is capital I of s is equal to 2 divided by s square. If you refer the table, you find that if f of t is equal to at, capital F of s is equal to a by s square, here a is equal to 2. Next, let phi of t is equal to 2 into e to the power of minus 5t volts. You know that this function is an exponentially decreasing function. For example, at t is equal to 0, phi t is equal to 2 volts, and at t is equal to infinity, phi t is equal to 0 as shown in figure. So, the Laplace transform of phi of t is equal to 2 into e to the power of minus 5t is capital V of s is equal to 2 divided by x plus 5. How is this? If you refer the table, you find that if f of t is equal to e to the power of minus at, its Laplace transform f of s is equal to 1 divided by s plus a. Friends, now let us study the process of transforming the circuit elements such as resistance, inductance and capacitance. Consider a resistance of R ohms connected across a time varying excitation V of t volts as shown in figure. Let I of t be its response. The balance equation for the circuit in time domain will be phi of t is equal to I of t into R. This we know. By taking the Laplace transforms of voltage and currents, we get capital V of S is equal to capital I of S into R. So, we get R of S is equal to V of S divided by I of S. This we can call it as a transformed resistance, or G of S is equal to I of S divided by V of S. Since we know G is equal to 1 upon R, therefore G of S is a transformed form of conductance. Hence, the transformed network in frequency domain can be drawn as shown in figure. Next, consider an inductance circuit element connected across a time varying voltage as shown in figure. Let the response be I of t amperes. The balance equation for the circuit can be written as V of t is equal to L into di by dt. By taking the Laplace transform, we get V of s is equal to L into Si of s. Note that the Laplace transform of d by dt of f of t is equal to s into capital F of s minus f of 0. Here we assume that the initial current through the inductance is 0, so we get V of s divided by I of s is equal to s into L, or ZL of s is equal to s into L, where ZL of s is the transformed impedance form of inductive reactance. Similarly, YL of s is equal to 1 upon SL, where YL of s is called as the transformed admittance form of inductive reactance. Note that. If you keenly observe, friends, the equations we have obtained and recall what we have learnt in basic electrical engineering, you find similarity. There we represented XL is equal to omega L ohm, isn't it? Here XL will be called as inductive reactance in ohms. Now, if XL of S is equal to SL is equal to j omega L, and if S is equal to j omega, then this XL of S we call it as a transformed form of inductive reactance. That is simple. So, the transformed network in frequency domain can be drawn as shown in figure. You see that circuit in the time domain and circuit in the frequency domain is exactly same, but note that all the circuit elements, voltage, current, all are transformed form in the frequency domain diagram. Friends, next consider a capacitance circuit element connected across a time varying excitation as shown in figure. Let the response be I of t. For the above circuit, the balance equation can be written as I of t is equal to C into dV by dt. This you know. By taking the Laplace transforms, we get capital I of s is equal to C into S into capital V of s. Here also we assume that the initial voltage across the capacitor as 0. So, V of s upon I of s is equal to 1 upon Cs, or Zc of s is equal to 1 upon Cs, where Zc of s is the transformed impedance form of the capacitive reactance. Similarly, Yc of s is equal to Cs, where Yc of s can be called as a transformed admittance form of capacitive reactance. Similarly, if you observe this equation also and recall the vector form of capacitive reactance, we represented Xc is equal to 1 upon omega c ohms. Now, if Xc is equal to 1 upon j omega c and Xc of s is equal to 1 upon Sc, and if s is equal to j omega, this Xc of s we call it as the transformed form of capacitive reactance. So, the transformed network in frequency domain will be as shown in figure. Here also you see that the circuit is same as that of time domain circuit, but all the quantities in the transformed network are in the frequency domain. To emphasize the concept we have learnt, let us solve one problem. In this problem, we are required to find the input impedance of the given circuit. If you observe the circuit, phi of t is the excitation applied and I of t is the response. We know that the input impedance Zin is equal to phi of t upon I of t. By observing the network, we find that the circuit elements in the network are 4 ohm and 0.5 farad are connected in series in one branch. Let Z3 is equal to 4 plus 0.5 farads. Next, 4 ohm is in the other branch. Let Z2 is equal to 4 ohm. These two parallel branch equivalent is in series with 2 henries. Let Z1 is equal to 2 henries. How do we find Z in now? Only the way is to transform the given network using Laplace transforms. We know that the Laplace transform of phi of t is capital V of s, I of t is capital I of s, and Z1 of s is equal to 2s, and Z2 of s is equal to 4, Z3 of s is equal to 4 plus 1 upon 0.5s. Note that. By solving it, we get Z3 of s is equal to 4s plus 2 divided by s. But Zin of s is equal to Z1 of s plus Z2 of s in parallel with Z3 of s. By substituting the values and solving, we get Zin of s is equal to 8s square plus 10s plus 4 divided by 4s plus 1. Of course, here Zin of s is in the transformed form of the input impedance Zin. Hope you got the skill of transferring the given network. We shall solve some more numerical examples in the subsequent tutorials. Friends, during this tutorial, we have learnt only the introduction to Laplace transforms. Of course, this tutorial will serve as a foundation to apply the concepts learnt to solve system equations we obtain in a time domain. So, I happily welcome you to my next tutorial on applications of Laplace transforms. You will enjoy them. I hope this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.